スタンダード4、CHERI-RISC-V ということで、当社Codasipのタリックの方から、RISC-V の標準化の動向についてお話しさせていただき、CHERI-RISC-V の標準化の動向についてお話しさせていただきます。
はい。So for I would like to Tariq Kurd, he's a distinguished engineer and lead IP architect at Codasip Design Center in United Kingdom, and he will talk about the trend of CHERI-RISC-V standardization.
Okay, Tariq, please start.
Okay, can you see the slides?
Yes.
Yes.
Go ahead.
Good, thanks. Okay, so my name is Tariq Kurd. I work for Codasip in Bristol in the UK, and I have been looking at CHERI for several years now, and I'm very involved in trying to standardize CHERI to make sure everybody can use it. So, as a brief introduction, which I guess is not really required, as you've just heard John with his excellent presentation, but very quickly, to say that CHERI is providing deterministic memory safety. So this is something we all need, and memory safety problems are something we all suffer from with malware on our computers. And one of the most famous exploits in the last few years is the OpenSSL Heartbleed bug, where the losses are estimated to exceed $500 million. This was an exploit where a server was tricked into returning the contents of its memory, including passwords and other secret information, simply by asking for it to return too much information, more than it was supposed to, because there was no memory checking, no memory safety implemented. The server was quite happy to return the contents of the information and therefore leak secret information. So memory safety is something we all need. You may have noticed that if you use the Chrome browser, it gets updated every week, and that's because exploits and vulnerabilities keep being found and it keeps being patched. So we need to work towards having much more safe and secure computing for everybody. So I'm in the UK. CHERI is part of the UK semiconductor strategy. So we have been in contact with the government to try and make sure that companies implement memory safety, and it's even been mentioned by the White House in the US and is, I believe, recommended. Okay, so as John mentioned, CHERI does exist in various forms. As I work for a company, this is what we have. This is the world's first CHERI-RISC-V application core. It's called the Codasip X730. It's an in-order dual-issue core with 4 ALUs, 2 early and 2 late, and it supports 100% compatibility for RISC-V binaries, and it also has full support for the latest version of the CHERI standard, which is on GitHub. So we're also very active in porting the software along with our colleagues in the CHERI Alliance, most notably Cambridge University. And so, as we can see here, we have an early version of CHERI Linux up and running. Obviously, Cambridge University have done excellent work on porting CHERI BSD, and now we're moving to a more mainstream Linux platform that people tend to ask for. It's also worth noting that CHERI is really good at detecting programming errors as well as exploits. So it's just having it included in your processor is just a very, very good thing to do. Okay, so very, very quickly, again, because John's talked through this excellently before, so I don't need to say very much. Without CHERI, you can basically, any integer pointer can at least attempt to dereference any memory location. If you have virtual memory implemented or physical memory protection, then there will be some coarse-grained protection in there, but it's coarse-grained, it's not exact. What you really want is, if you've requested some memory, you've requested 48 bytes for a string, and then you're returned a pointer, that pointer can only access the 48 bytes and nothing else. You cannot access the 49th byte, and you cannot go the wrong way in memory and access the byte before the string either. So CHERI gives us this. It allows capabilities to only access the bytes which are permitted and nothing else. And in contrast with memory tagging, it is deterministic and it is precise. So you get a precise exception as soon as the problem happens. Okay, and again, John's already said, so I'll go quickly. CHERI exists on multiple architectures already, originally on MIPS. The RISC-V, which we're using for the proposal for standardization, came from the CHERI V9 architecture, which we've been working on for about the last 3 years now to make it fit really smoothly with the RISC-V architecture. x86 has a prototype sketch as well, so it's definitely not single architecture. CHERI exists, which is a small version for embedded devices originally developed by Microsoft Research, and its specification has been different, but we've been converging the specification so that the 0.9.5, which we have as our proposal for standardization, is also compatible with CHERI. And our plan is to standardize CHERI for the whole range of calls, from tiny IoT calls all the way up to application and server calls. So, as I said briefly, we're currently at spec version 0.9.5. We have submitted this to RISC V International for architecture review. The specification is currently in a stable state, which means more or less bug fixes only. Other changes are unlikely, and we are waiting for review feedback from them. And the intention is that this becomes a ratified standard by the end of the summer or early autumn this year. Many things have changed since the original CHERI V9, which was developed mostly by Cambridge University, and an important thing is we have brought it forward to be compatible with RVA23, which is the latest RISC-V profile, which has some notable and quite pervasive changes in it, where you must support vector processing, you must support a hypervisor, and you must support pointer masking. It also has other nice features we've introduced recently. To be fair, I mean, these are features are typically in other forms of CHERI. We have the load mutable, which I'll talk about later, capability levels, so you can control how far capabilities propagate. We allow alternate capability formats, not least because CHERI has a different format. We've added some instructions, including guessing the mode and the capability type and easy mode switching. We've improved the way we handle CSRs in integer pointer mode, which is the compatibility mode. We've very recently sorted out compatibility with the ZI LSD, ZC LSD, that should say, newly ratified standards, and various other things as well. The objective is to have as many of the proven CHERI features as possible and be compatible with RISC-V and to run RISC-V legacy binaries. Ooh, I need to speed up. Okay, so very quickly, we've added some bits to the page table entry. So if you support virtual memory, we need to be able to have revocation sweeps on memory to prevent use after free problems. So we add 2 bits. By default, no memory can support written tags, so you can't just randomly store tags, capability tags to memory, which is controlled by the CW bit, the capability write bit. So if your OS does not support CHERI, then user space code cannot store capability tags. And there's the second bit, which is the capability regeneration used for revocation sweeps, which is currently just for user mode, and we may do kernel mode in the future. We have the thread identification model for compartmentalization. Compartmentalization is a key feature of CHERI, which involves being able to run code in secure sandboxes which cannot interfere with each other. The secure thread allows each sandbox or compartment to explicitly identify itself and to know exactly where it is and never be confused. Something that's changed recently is we've added in the hypervisor support for CHERI. The hypervisor and CHERI combination already exists in Morello. Hypervisor has been implemented on CVA6 open source. As far as I'm aware, that does not also include the PTE bits. So I think there's a bit more work here to do on the proof of concept. But essentially, we add in something called the CHERI register enable to enable or disable CHERI, which we have at different levels of privilege already. And this is extended in the hypervisor, so you can have guest OSs which support CHERI and others which don't. And we currently have no support for CHERI in the second stage page table entries at the moment. That would be future expansion. We've introduced support for pointer masking in CHERI. So we've altered the bounds decoding to support pointer masking, and changing the number of masked bits affects the meaning of the bounds. So these are both fairly recent features. Vector in CHERI is more interesting. So there are proposals to actually store capabilities in vector registers. We haven't specified that yet. That's future work. So what we have done is made the CHERI specification compatible with the RISC-V ratified vector specification, where the checking that we do on every memory access only applies to active elements, because vector allows elements to be masked, and so if an element is masked, it must not cause exceptions. And so in the extreme case, on a vector load or store, if every element is masked, then there can be no exceptions, definitely no CHERI exceptions. There's something in the vector spec called fault-only first loads, where only element 0 can cause an exception, and so you will only take a CHERI exception on the fault-only first load if the exception affects element 0. If element 0 is masked, you never take an exception, even if the authority capability has no valid tag. Then you reduce the vector length instead. This will make sense if you understand the vector spec. So the two things need to be understood together. Okay, we have another feature, which again is in previous versions of CHERI, called load mutable, where essentially you can make read-only copies of data structures. It prevents you from having to make deep copies of data structures by passing a pointer to someone else and saying, here is my pointer to my structure. You can only see the entire thing read-only, and when you follow pointers through the structure, you only get read-only copies, which is a very powerful feature. We also have CHERI levels, which is local and global, which again is in CHERI v9, Morello, and Chariot. This is to control, in a way it's similar to the load mutable, which is for making read-only copies. This is to prevent how far capabilities can propagate. So you can pass a capability on, but then you can't pass it on again. So it controls the propagation. These are very powerful features which are generally missing in computer architectures. Okay, we have a lot of extensions. We have, so CHERI, all of these names are temporary because we haven't had them reviewed yet. But we have PureCap. PureCap is the CHERI machine. It's the base architecture. When you build a CHERI machine, the first thing you implement is PureCap. So that runs the CHERI code, and will, if you just run standard RISC-V binary in a PureCap machine in PureCap mode, it will behave differently. As an addition, we support the hybrid mode, so this is where we switch into legacy RISC-V support, so we can support existing RISC-V binaries with 100% compatibility, and so we can jump to a precompiled library which is in existing RISC-V code, run that in its own compartment, and then jump back to a PureCap kernel, for example. We also have some smaller extensions like the shift4 add, because the native data type is 16 bytes on the 64-bit machine. We need to be able to shift one more place, so this is a code size reduction and performance improvement. Standard RISC-V includes shift 1, 2, and 3 add. We have byte and a half width load reserved store conditional. This is because typical load reserve store conditional will set a reservation on a larger data type, but you can't access outside the CHERI bounds. So if you're only trying to access a byte, you can't make a wider width. So we need smaller width versions. Pardon me. Okay, so the ones in green are very, very stable. The ones in blue are also included in the 0.9.5 specification, but are still in the software prototyping. So we have SVUCRG, so this is the capability read generation for user space code, which is for revocation sweeps, as mentioned by John before and myself earlier in this talk. We have the secure thread ID, which is used for compartmentalization. And we have levels, as mentioned before, which limits the propagation of capabilities. So around all undergoing software prototyping. We have too many ideas for future extensions, but one is to have optimized memcopy supported by the vector unit, which implies you need to have capabilities in vector registers, as an example. Okay, so for RV32, I ratified the code size reduction extensions. I spent several years on that. And so I've added in support for ZCMT, which is table jump. So in this case, the table jump is where you make a dictionary of function pointers and put them in memory. And so you replace your function pointer in your code with a 16-bit encoding, which indexes the table. To make that CHERI compatible, the JVT, the jump vector table, which is the base pointer of the table, becomes a capability, so you can only jump successfully into that range. There's ZCMP, push pop, where the data width doubles, so essentially you're using the RV64 format instead of RV32. Okay. So in conclusion, CHERI, we already have CHERI up and running with Linux on our in-house RISC-V core and with full RVA22 compatibility, which is the previous RISC-V profile. We've updated the specification to be 100% compatible with RVA23, all the mandatory extensions. Some of that is still undergoing software prototyping, but we believe that the specification is good. CHERI runs existing RISC-V code with 100% compatibility if you implement the legacy hybrid mode, which we call integer pointer mode. So it means you can take your existing binaries, you can run them on a CHERI core, and you can have a path to memory safety without having to change all of your code immediately, or in many cases just recompile. And the specification is set up to be a base for CHERI as well. It's important to have CHERI compatibility. So in the future, all the new Codasip cores will have CHERI. The CHERI Alliance is here. Mane spoke about that earlier. And the idea is to have CHERI world domination where all the cores are memory safe. So it becomes much, much harder for exploits. And this is my final slide. So come and visit us on GitHub. This is where the spec is, github.com/RISC-V/RISC-V-CHERI. All interested companies should join the CHERI Alliance and join the working groups and get involved. You can join the CHERI TG, the RISC-V CHERI TG, the bi-weekly meeting. You can tell us what's missing in the CHERI specification and help us fill in the gaps, help us develop it, and help drive CHERI to world domination. And that's it. Thank you. Thank you.